Hi, my name is Dan Elton, and I'm going to be talking about my paper, Self-Explaining AI as an Alternative to Interpretable AI. But before I start, I have a disclaimer. I am speaking here in my personal capacity. The opinions expressed here are my own, and they do not reflect the view of the National Institutes of Health, the Department of Health and Human Services, or the United States government. So when we're talking about explainable AI or interpretable AI, people have very different ideas about what the term explanation means. So in my paper, I distinguish three different types of explanation. There are more fine-grained distinctions that could be made, but these are three high-level distinctions. First, we have what we might call conventional explanation. And this type of explanation is descriptively accurate in that it reproduces the input-output mappings to some degree. And it is also relevant to the end user. So it provides information which is considered understandable and actionable for whatever use case the model may have. This contrasts with the meaning of the term explanation that we might have in physics, which would be providing a mechanistic explanation. So with mechanistic explanation, we are not going to reproduce all of the computations, but we're going to provide some kind of approximate high-level theory as to the mechanism that is used. And this is important because models with very similar input-output mappings can have very different mechanisms. So it's been shown that for any given data set, many models exist which have the exact same accuracy but very different mechanisms internally. Finally, we have the meta-level explanation. And this is an explanation in terms of the process of how the network was built. So to understand how a network was built and trained, you need to know the data set, the network architecture, the learning rules, and optimization method, and the objective function. And we can understand a lot about neural networks just from understanding these precursors. And this type of explanation is analogous to how the theory of evolution explains animal behavior. Similar to how animals evolved to maximize their reproductive fitness, these neural networks, when they are trained, they maximize their objective function. So I think mechanistic explanation is extremely important for building trustworthy and robust AI. And there's a pretty simple reason for this, which is that we want to have some idea whether these models can extrapolate. And we can only really understand that if we understand the mechanism. So for instance, with this parabolic curve, if the model was really using this parabolic function, we know it would be able to extrapolate. But there are other models which would fail to extrapolate. And by understanding mechanism, we can also understand how robust the model might be to anomalies which might arise in the real world. So for instance, in medical imaging, there are many anomalies that can come in, like having implants or different scanner settings or contrast in different organs. And if we had a firm grasp of how these black box models were working, that would help us to be able to trust that they are going to perform well in the field. So here's an example I discussed in my paper from my own work, where I was trying to label these vertebrae in the spine. And I was really curious whether the model was looking at these ribs, because the way a clinician would label these vertebrae would be by looking at the location of the ribs. And so if the network was using the ribs, that would be a very robust method. Whereas if it was using locations of different organs, that would not be nearly as robust. So for understanding neural networks and doing interpretation, there's been a huge number of methods proposed. And I haven't gotten to read all of these papers in detail, but I was able to sort of categorize them into several different types of method. And I also highlighted some of the most popular in red. So in actual practice, the most popular are the saliency maps and also this LIME method, which involves fitting local linear models. But there's some major problems with saliency-based methods. There's a great paper called Sanity Checks for Saliency Maps. And one of the things they show is that when you start randomizing different layers in the neural network, the interpretation heat map often will not change. So as we go left to right here, we're randomizing more and more layers starting from the topmost layer. And what we see is that with a lot of these methods, the interpretation doesn't really change. So it seems like with some of these saliency methods, really what they're capturing is just what's going on in the very lowest layers, which is essentially edge detection. Another problem with saliency maps is that they show you where the network is looking, but they don't really show what the network is doing. So this is a great example here where we're looking at this saliency map for the prediction of whether this image is a Siberian husky. And so the evidence that it's a Siberian husky is somewhere in this red and yellow region. But we can also look at the evidence that this image is a transverse flute, and we see it's in a similar region. So just on the basis of these maps, we can't really tell what specific features here are leading the network to, at the end of the day, classify this as a Siberian husky rather than a transverse flute. So these saliency methods can be rather deceptive, and they often don't provide as much information as we think. There's other problems that have been noted with many of these methods. For instance, LIME seems to be very sensitive to noise, and also the tuning parameters that are used in the LIME algorithm. And then it's also been shown that with saliency methods, they are very susceptible to adversarial attacks. So by adding a few pixels into this image, you can completely manipulate the explanation. So now I'm going to shift gears and I'm going to go into the phenomenon of double descent, which I think really helps us understand how these neural networks function and why they're hard to interpret. So for a long time, there's been a number of very curious facts noted about deep neural networks. They often have 10 or 100 or 1,000 times as many parameters as training points. So by conventional wisdom, they should be greatly overfit. It's also been noted that many of these models fit their training data exactly. So again, we would expect them to be overfit, but they still generalize very well. And then it's also been found they are robust to huge amounts of label noise. So the phenomenon of double descent and direct fitting can help us understand all these phenomena. So here's the stereotypical double descent curve. The training error is shown in green, and the test error is shown in purple. And on the x-axis here, we are varying the width of the layers, which controls the number of parameters. So as we increase the number of parameters, what we see is that the test error first drops and then it starts to increase. And this is what we expect from the Bayes variance trade-off in classical statistics, where as we increase the number of parameters, at some point we've reduced our bias, but now our variance is increasing a lot. So we get overfitting and the test error starts to get worse. So that's really interesting, but then if you continue, you'll see that at some point this curve actually turns around and the test error starts decreasing again. And this is the double descent phenomena. So here's a few little tidbits on double descent. Part of the reason that people generally didn't notice this was that it can be hidden by the practice of early stopping in training, which is very common. And it's also been found in other models, such as decision trees and Fourier series models. And there's a sense that it's sort of almost a universal principle for machine learning. And it was proven analytically a long time ago for certain types of single-layer perceptron. And another interesting point is that it's believed the brain may operate in this regime of where it's gone past that peak, which raises a lot of questions about kind of conventional thinking in neuroscience, where conventionally it was thought that the brain just didn't have enough data to do this kind of interpolation that I'm going to describe. So the way that double descent works is very well captured by this figure from Hassan et al., where we're trying to fit a parabolic curve to some noisy data generated from a parabolic function. And so the ideal fit here would have 3 parameters. When we start to add more parameters, we get this overfitting, which is characterized by this overshoot and undershoot. But the interesting thing is if we add more and more parameters, at some point we get what they call the direct fit. And this is where we have almost like a piecewise interpolation between the data points, which is smooth and does not have this overshoot or undershoot. So we can notice some interesting things about direct fitting. The computations are local, and they almost are like nearest neighbors type computation. And the global trend here is not really being extracted. And there's not really any hope for generalization. However, on the other hand, this kind of procedure can fit almost any data. So if this curve was to suddenly drop down, it would have no problem fitting it. So these models are extremely flexible, but the flexibility here also makes them hard to interpret. And what I argue in the paper is that a lot of the narratives that we have about deep neural networks don't seem correct in light of this. So the idea that the deep neural networks are extracting these high-level features and then making predictions and classifications based on those doesn't seem right. It seems like really what they're doing is they're doing just brute force interpolation. And if there happens to be a neuron which is, say, sensitive to like the ears of a cat, that's really just a side effect of the data. It doesn't mean that the network is basing its prediction on that particular neuron. Rather, what it seems to be doing is this interpolation between data points that it's memorized, essentially. And there's some other reasons that deep neural networks are hard to interpret, such as the observation that these networks are very hard to compress. And that's not surprising, because if the real world is complex, these networks are also going to be very complex internally. So in light of this and the difficulties with conventional explanation, I explored the idea of using self-explanation, meaning having the AI actually provide an explanation. And if the AI can provide an explanation in some human understandable format, that could go a long way to increasing our trust that the AI is going to function correctly. So this is a simple attempt at self-explaining AI, where these authors built a neural network to do detection and diagnosis of lung nodules in lung CT scans. And the nodules are classified as either malignant or benign. But then furthermore, they also predict these scores for different attributes. So there's 6 attributes which are deemed important for by clinicians for figuring out if nodules are cancerous or not. And they had some ground truth data, and they used that to predict these attribute scores. And then the claim was that the neural network is actually using these attribute scores. So whatever attribute scores is giving actually constitute an explanation of the diagnosis. But it's simply not clear whether this was actually what was going on, because it's quite possible that if you look internally at this neural network, the 2 branches are being computed very independently. So this is where I brought in the idea of using mutual information measures to determine if the output of that attribute branch is actually used or related to the diagnosis. And mutual information measure is very sensitive to any kind of nonlinear dependency. And so we look at the mutual information between the diagnosis output and the neurons in the latent layer, and we look at the mutual information of the attributes output and the neurons in the latent layer, and then we look at their overlap. So if there's overlap in the neurons used, that means different the attribute in question is related in some way to the diagnosis. And this is just sort of a first attempt at self-explaining AI. In the future, we could probably improve this. But there's also some other important things which I believe should be more standard for increasing trust in AI. The first is uncertainty quantification, which for a long time was not done through computational reasons, but now we know that Bayesian uncertainty can be approximated with dropout during inference. So there's really no excuse for not doing this now. But uncertainties can be wrong when extrapolating, just as the predictions can be wrong. So another component I think is important is applicability domain analysis, which is where essentially we have a warning light system which alerts the user if the input data falls outside of the training distribution. So there are many ways of doing this, but essentially what you're going to do is look at your training data distribution, and you're going to delineate the distribution and points that fall safely within the distribution from points that are outside the distribution. So here I've just drawn this red line around some of the outer points, but there are more sophisticated ways of doing this. So if you have a point that falls outside the distribution, then you should provide the user a warning. And there's some related ideas as well, such as change point detection and detecting anomalous inputs. So here's an example of a network where I put together these different components. So we have the diagnosis and uncertainty interval explanation and uncertainty, and then we have the applicability domain analysis and the neutral information analysis. And together these are all used to provide the final explanation and confidence levels. So in conclusion, current explainability methods can be misleading in many ways, and double descent and other considerations suggest that mechanistic explanation is very difficult. So we need these key ingredients for robust, trustworthy AI. We need the uncertainty quantification, applicability domain analysis, and self-explanation. And please, I encourage you to check out the latest version of the paper where I've updated a few things. And please email me if you have any questions. Thank you.